What we're going to work on in this session is the fundamental theorem of algebra, kind of, sort of. We're not going to use the mathematical lingo, but we are going to talk about what it means. The fundamental theorem of algebra says that a polynomial function will have exactly n roots if its degree is n, when you include several different things. We want to include rational roots. Rational roots would be like x equals 4, x equals negative 2/3, rational numbers like that. Multiplicities. Irrational roots. And complex roots. Now, irrational roots are going to include things like x equals 5 plus the square root of 3, and complex roots will include roots like x equals 2 plus 3i. Now, there's an important thing to know about irrational and complex roots, and that is irrational and complex roots always occur in conjugate pairs. So you will never have just one single irrational or complex root for a function. They'll always go together. So the conjugate for x equals 5 plus the square root of 3 would be x equals 5 minus the square root of 3. And for x equals 2 plus 3i, it will be x equals 2 minus 3i. So let's look at how to find all roots. Of a function, f of x equals 3x to the 5th minus 7x to the 4th plus x cubed plus 3x squared. So what we want to do is first kind of figure out how many roots we're looking for. Since the degree is 5, there will be 5 roots total. So when we've identified 5 roots, we'll be done with the problem. Let's start by seeing if there's a greatest common factor. If there's a greatest common factor, we'll want to factor that out first. And it looks like x squared is in common for all of those, so I'll rewrite this as x squared times 3x cubed minus 7x squared plus x plus 3. And from there, I can already identify 2 of my roots. If x squared equals 0, that means I have the root x equals 0 and the root x equals 0. So there's 2 roots. I have a multiplicity of 2 at x equals 0. Then I'm going to start breaking down this factor right here. And I will do that by listing my possible roots. These will be possible rational roots. To list possible rational roots, I want factors of the constant term. So that's this 3 out here. So plus or minus 1 and plus or minus 3 over factors of the leading coefficient, which is the 3 in front of the x cubed, plus or minus 1 and plus or minus 3 as well. And then I need to split that list. So I'll list the factors of 1 and 3 over the denominator of 1. So that will be plus or minus 1 and plus or minus 3. And then I'll need the factors of 1 and 3 over the other denominator of 3. So that will give me plus or minus 1/3. And then 3 over 3 would be 1. But since I already have that written, I'm not going to repeat it. So I have 2, 4, 6 possible rational roots. And then I will start testing. So let's say I test 3. So 3 goes, and I use the coefficients of 3, -7, 1, and 3. And again, I'm looking for this remainder to be 0 to tell me if this is a factor. So bring the 3 straight down. 3 times 3 is 9. Add -7 to 9, I get 2. 2 times 3 gives me 6. 6 plus 1 is 7. 7 times 3 is 21. And 21 plus 3 is 24. So it's not a root, but that does tell me that 324 is on the graph, in case I'm interested in graphing this later. Let's test another value. How about 1? So again, 3, -7, 1, and 3. Bring down the 3. 3 times 1 is 3. Add those, so I get -4. -4 times 1 is -4. Add -3, multiply again, and add, I get 0. So x equals 1 is a root. And then I will rewrite. So I still have the x squared from the beginning. Now I'm going to take that times the factor. Well, if x equals 1 is my root, then when I subtract 1 over, I get x minus 1 equals 0. So my factor is x minus 1. And then times the quotient down here, which remember that this term is the remainder. This is the coefficient that represents the constant term. This coefficient goes to the x term, and this coefficient will go to the x squared term. So that will be times 3x squared minus 4x minus 3. So this is now what f of x is. And I want to keep doing that list, test, rewrite until I get to a quadratic. And once it's quadratic, I will either factor, use a quadratic formula, or complete the square to solve. This one doesn't look like I can factor it, so I'll use quadratic formula. So I get x equals 4 plus or minus the square root of 16 minus 4 times 3 times -3 divided by 2 times 3. So that is 4 plus or minus. Inside the radical I have 16, and that's going to be added to 36, so square root of 52 divided by 6. Square root of 52 simplifies. 4 plus or minus 2 square root of 13 divided by 6. And then I can simplify each of these coefficients and the denominator by 2. So I get x equals 2 plus or minus the square root of 13 all over 3. Now this is, again, 2 roots. Those roots are x equals 2 plus the square root of 13 divided by 3, and x equals 2 minus the square root of 13 divided by 3. And there are those conjugate pairs that we talked about earlier. So we now have, we were looking for, again, 5 roots in this problem. So we have 1, 2, 3, 4, 5. Let's just look at one more quick example here. F of x equals x to the 4th minus 3x cubed plus 5x squared minus 27x minus 36. So again, I want to know how many roots will there be. I look at the degree of my problem, that's 4, so there will be 4 roots. So by the time I'm finished, I should have 1, 2, 3, 4 roots listed here. Let's check to see, is there a greatest common factor for each of these spots? And there's not. The only one is 1, so I can't factor anything out. So then I will list my possible roots. Again, that's factors of the constant term, 36, over factors of the leading coefficient, which this time is 1. So let's see what happens when the leading coefficient is 1. I'll have plus or minus 1, 2, 3, 4, 6, 9, 12, 18, and 36. Man, 36 has a lot of factors. And then over the factors of the leading coefficient, which happens to only be plus or minus 1. So when I split that, it actually only ends up being all of those factors of the constant term. So if your leading coefficient is 1, that cuts down your work by quite a bit. And in fact, I would not do this first step most of the time, but I just wanted to show you what that was like. So we listed, now let's test. Let's see, if we were in class, I would be asking you what numbers you want to test, but since we're not, I guess I'll start with 2, I guess. We use the coefficients here, 1, -3, 5, -27, -36. You want to make sure that if you have any missing terms, you use a placeholder of 0 in that row. We bring down the 1, multiply, we get 2, add -1, multiply, -2, add 3, multiply 6, add -21, and when I multiply that, that is not going to give me a root. So let's go on to 1. 1, -3, 5, -27, -36. Let's see, 1, 1, -2, -2, 3, 3, not gonna happen, right? How about -1, 1, -3, 5, -36. If you're a good guesser, this goes faster. I'm not a very good guesser. 1 times -1, -1, add -4, multiply, +4, add 9, multiply, -9, add -36, multiply, +36, and we get 0. Good. So one of our roots is x equals -1. So I'll write that up here, x equals -1, and then I will rewrite. So remember that if x equaled -1, I add that 1 over to get x plus 1 equals 0. So my factor I'll rewrite as x plus 1 times the quotient. Remember, the last number is the remainder. Then we have the constant term, the x squared term, the x cubed term. So this will be x plus 1 times x cubed minus 4x squared plus 9x minus 36. Okay, we're off to list, test, and rewrite. And you'll notice we have the same constant term and the same leading coefficient. So we can just continue testing from our list. Since 1 and 2 didn't work before, they still won't work. So let's try, I guess I better write that down. List is the same as before because we still have 36 and 1 there. So then I'll start testing. So I'll try 4. And now I want to use the smaller row. I don't want to go back to the original problem. So I'll test with 1, -4, 9, and -36. So bring down the 1, times 4 is 4. Add, I get 0, times 4 is 0. Add, I get 9. 9 times 4 is 36. So there is a root. We have a root at x equals 4. X equals 4. And then I will rewrite. So I have the x plus 1 from the first root. X equals 4 gives me a root at x minus 4 for the factor. And then this row, remainder, number, x squared. So that will be x squared plus 9. And then this is going to be a quadratic. So actually if I set that equal to 0, I can subtract 9 from both sides. That gives me x equals -9, x squared. Square root of that would be x equals plus or minus, the square root of -9 would be 3i. So there are my other two roots, x equals 3i and x equals -3i. And I have found all 4 roots. I also just want to point out that you could factor this by SOS.